Hello, my name is John Shuey, and I'm going to be presenting on behalf of Team 1, our Facility Access Control System. We were very grateful to be able to work with GE Vernova in this cyber-informed industrial project. Now, what exactly is a cyber-informed industrial project? As many of you know, cyber attacks have been on the rise, not only in our homes, but also in industrial environments. Because of the rise of cyber and network attacks on industrial systems, there is an ever-growing importance for engineers who are designing these systems to have a cyber-informed mindset in their design process and to make their systems robust against these kind of attacks. Project Charter was to build a security protocol model that combines computer vision together with GE's flagship Mark 6E controller. The door will be secured using two-factor authentication, facial recognition, and voltage monitoring by April 16th of 2025 for $5,000 or less. This will be implemented in conjunction with two other teams which are sharing the Mark 6E controller. As you can see from the implementation model before you, we have a two-door system with an LED tower and a user interface tower. Now, door one is our threat model and the system that is the primary interface together with the authentication and the RFID two-factor. The UI tower houses our depth sense camera as well as the touchscreen LCD for user interface and the RFID badge scanner below. The LED tower simply displays the three states of our system. This is controlled by the Mark 6E controller, not shown. Each state represents a waiting state, or the green, which is authentication passed, or an alarm state if we detect that a threat has been launched and that door one is compromised. As you can see from the block diagram of our system, the goal of having two different controllers is to have the Raspberry Pi have complete control of the first door and have it responsible for passing the two-factor authentication in the form of facial recognition and RFID, and only then will the first door open. Now, our malware model is one such that the user, when they execute the reverse shell, can control the first door at will without going through our authentication protocol. The idea is that then our voltage regulation system, which is monitoring the input to the motor controlling our first door, will be able to flag that something has gone awry and prevent the Mark 6E from opening the second door. So we have two control systems, one which implements two-factor authentication in the form of facial recognition and RFID, and a second system which receives an input from our hardware circuit to verify that this process has been properly achieved in order to open the second redundant door. We 3D modeled this physical structure. Both doors are hinged by two digital servo motors, which are 0 to 180 degree operation. The Raspberry Pi, as I previously stated, has complete control of the first door, and while the authentication and our voltage regulation system are necessary as inputs to the Mark 6E to control the movement and the logic for the second door. Our cybersecurity features include the RFID reader, facial recognition, depth sense to prevent spoofing, and we also implement voltage monitoring to combat cyber attacks all the way down in our hardware. A picture of what that circuit looks like can be seen in this circuit diagram. I'm taking the PWM input to the first servo motor, which controls the operation of the first door. I have to filter that signal in order to get a DC approximate value. I then set a reference voltage, which can change depending upon whether or not the authentication has been passed. The logic here is that the reference will be set low to just above the 0-degree position of the servo motor, so that at any point if the servo motor trips without authentication being passed, the comparator will be driven to the positive rail, sending a flag signal to the Mark 6E and triggering our alarm state, which will result in red light and the prevention of the second door operation, which will remain closed even if the first door is exploited.
First test is a unrecognized RFID badge. Does not allow access, does not allow the user to go to facial recognition. Now,
to quickly go over the software used in our system, it consists mainly of two scripts. The first and most simple is the relay script, which takes a digital input pin from the Raspberry Pi and listens on it. The Mark 6E will then send a high or a low voltage that indicates whether the door should be open or closed. High represents open, while low represents closed. This is so that the Mark 6E has control of the second door, as the Raspberry Pi is the only thing that can actually control the PWM values sent to the servos. The next is the main authentication script. This consists of 3 different states or processes. The first is the RFID process. In this process, it simply waits for the RFID to be scanned and for a valid one to pass to the next state, which is facial recognition and depth sensing. Facial recognition is implemented through OpenCV and the face recognition models. The face recognition models use something called Euclidean distance to produce matches. So first, a database of faces are encoded, and then when an image is passed to facial recognition, it will re-get these encodings and compare them using Euclidean distance. A low distance means that this person matches, while a high distance means that this person does not match. I should note that this occurs for every face within the database. Using this, you can actually see who this person matches. Next is depth sensing. So depth sensing occurs after facial recognition to ensure that the matched person is actually who they say they are. Depth sensing was used using the D435i depth sense camera by Intel and the Intel RealSense SDK. So this camera will pass both the RGB image and the depth image, which is aligned so that you can get the coordinates of the RGB image and align them with the depth. Using this, you can then take points on the RGB image and get the depths at those points. For our system, we use 4 distinct points, that being the nose, the user's 2 cheeks, and their neck. The nose must be the closest point, the cheeks must be in the middle, and the neck must be the farthest point, and there's also some checks to make sure that they're not too far apart.
next we will try multiple faces. So John will scan. I will hop in the frame.
Sorry.
Multiple faces detected.
So even though we're both members of Team 1 and we're both authorized users, it won't allow 2 people to scan at the same time.
But now, if we scan and there's no one in frame, no faces detected.
Next, I want to go over the GUI. So this first image goes over the RFID state. On the left, it is waiting for someone to scan their badge, while on the right, it is outputting that an unrecognized badge has been scanned. If a recognized badge is scanned, we move to the image state. In this state, a small box is output to the user to allow them to see where they should place their face to best get matches as well as depth sensing to occur. Once a image is taken, we go to the result state. These 4 images are the negative results, where you would not authenticate. Top left is no faces detected. Top right is an image taken with no one that's in the database being taken. Bottom left is if there is multiple faces, which in this case I did using a spoofed image as well, but that does not matter. And the bottom right is for a team/face mismatch. So even though I am a registered user, I am not a member of Team 2, which is the badge I use to scan into the system. The final thing I want to show off is the spoofing and the actual results. So on the left, it is a true image of me, and I have used the right badge, which is Team 1, so I am welcomed into the system. In this case, the doors would open. On the right is a spoofed image of Steven, and although I used the correct badge, that being Team 1, the program correctly identifies this as a not real person. It is a phone screen, so spoofing detected is output to the display.
Now, a recognized badge will be scanned, but the face of someone who is not on the team will show up. So John is not a member of Team 2. We scan Team 2 badge. Next.
Hello, I will now display how the malware works on the system. So we're going to assume that the malware successfully got onto the system due to a physical deformity. And for sake of showcase, we will not be hiding it. We will just have this directory called malware. So what will happen is through a mistake made by the system operator, the malware will be ran through adding this script at the end of a random file that is normally ran, and it's called persistence.shell. And I'm going to run it. And now the malware has already been activated. So what does this malware do? As we can see in this Vim, what persistent shell does is create a system daemon that consistently calls this executable script, which is right here. And what this does, and then it makes it a system daemon, therefore it's always running in the background. And we will see right here in this right here that it's already running and it's successfully running. Now what does this do? What this does is simply always run reverse shell. Just always run this Python file, which is here, that is always requesting to a host port, a host and a port on a secured server for this project to be a reverse shell. Request std in, request std out, and request std error. And so this is what the malware does. It's a shell script that sets up a system daemon file to always run an executable. That executable will always call this reverse shell.py. Thank you.
Next, John will try to spoof with the correct badge for Team 1. Since he is on Team 1, we will try to spoof. Spoofing detected.
The HMI also displays current live values from the system, such as if the authentication has been passed, the state of the voltage monitoring comparator, if the door to is open, and then also if the system is in the open state, idle state, or alarm state. Here you can see the HMI for the Mark 6E controller. You can see that you can turn the manual control on the left, and then control the opening or closing of the second door, and you can see that the values are updating on the right side.
So with the overview of the system complete, I want to go over some of the drawbacks of the system. The first and main drawback is that the Raspberry Pi has complete control. Because we were unable to get the Mark 6E to work and create PWMs for the servo motors, the Raspberry Pi has control of both motors. This is a big security flaw, as someone with access to the Raspberry Pi basically has access to the full system. We didn't account for this with our project, simply because the plan was to use the Mark 6E to create these PWMs, but it just was not possible. Next is sophisticated spoofing. So with the way our current depth sense algorithm works, there are ways to get around it, specifically because all it's doing is ensuring that someone is human. Things such as 3D printed faces or masks may fool the system because they would have the depth that the system is looking for. Next, I want to go over some future improvements. So, obviously, with the depth sense algorithm being discussed before, we could create a more robust one. The best case is that while onboarding, we could take depth measurements for every user and use that as what we compare to along with the facial recognition. This would mean that you would need an insanely accurate 3D model in order to get through. We could also implement something like liveness detection, which would ensure that a mask could not be used. Next is physical security hardening. So at this time, there are no locks that actually secure the doors, and instead it's basically secured through the servos pushing back. This means that a user could push through the system if they are able to overcome the servo motors. With this being said, I would like to conclude with a demo which goes over a user successfully authenticating in the door and a malware attempting to attack it.